with a new subtopic, which is not sure if it's a subtopic or a new topic. But it's I think it is a subtopic of energetics, and that's entropy. Now, this is going to be totally different from whatever you've studied. I mean, it's not really related to energetics. It's a completely conceptually, it's completely different. So we're going to learn about entropy, which is Uh, I mean, you might have heard about this in. I mean, you haven't studied about it, that's for sure, because it's not really taught at an early stage. Uh, Entropy is a very important concept. It's a very powerful and a very important concept. It's a lot more important concept than whatever you've studied in energetics. Actually, uh, entropy literally means it means it's a measure of disorder of a system. So next time when you hear the term entropy, it simply means disorder. Like if your room is really untidy, that means it has a very high entropy. If your room is really neat and clean, that means it has low entropy. So remember the concept. So high entropy means very disordered. Vice versa, low entropy means very ordered, and you can apply it to any field anywhere. You can apply this concept anywhere. So you've got high entropy states and you've got low entropy states. I'm just going to write down the unit for entropy. It's S. Standard entropy, you got a not on top of it. Standard entropy is simply entropy measured at room temperature. That's what standard entropy is, and it's the unit for entropy is joules per mole per Kelvin, or joules per Kelvin per mole, which is the same thing. So it's joules per Kelvin per mole. That's standard entropy for 1 mole of a substance. Uh, so measure of a disorder of a system, highly ordered state and very disordered state. Let me just copy one diagram if I can locate it. High entropy state. Just one second. High entropy state. High entropy state. Anyways, I'll just make my own diagram very quickly. Um, so you've got high entropy states and you've got low entropy states. Now, systems, whatever systems, let's talk about entropy generally first. You have all sorts of systems. Uh, so the first thing is you've got a neat room. Okay, let's apply it to a room. Okay, because we just want to figure out the concept first. So you've got a neat and tidy room, and you've got an untidy room. And let's say your room is the system. So the system is changing state. It's going from a very neat and tidy room to an untidy room. So it's changing its entropy. And it might be coming back as well. Okay, that happens very frequently. Okay, during the day, you might be tidying up your room and it would become untidy over the day. So so entropy is changing all the time. So that's a low entropy state, and that one over there is your high entropy state. So you can apply it to chemical reactions, you can apply it to economics, you can apply it pretty much everywhere. uh, so low entropy states, high entropy states, this is known as delta S. Delta S, I mean, you know what delta is. Delta stands for change in entropy. So delta S is positive if the entropy increases. Like if your room becomes dirtier or it becomes more untidy, that means delta S is positive. That means it's going towards a high entropy state. And vice versa, if you're tidying up your room, that means delta S is negative. That means you're going towards a low entropy state. So delta S stands for change in entropy or disorder. And delta S, if the sign is positive, that's the first thing. If the sign is positive, that means entropy increases. That means disorder increases. So you have many chemical reactions where this happens, disorder increases. And the other one is that delta S could be negative as well. So that means entropy decreases. So is this concept clear to everyone? Kosa, is this clear? Minail, is this clear?
Yes.
Yeah.
Yes.
Actually, now can anyone tell me which one is easier? Delta is positive or delta is negative? Like,
Positive.
okay, so positive is kind of easier. I mean, your room. I mean, it. I mean, your room kind of it would feel to you that it wants to be untidy. I mean, you don't do special effort to make it untidy. It just becomes untidy by itself. So things, and that's a universal law. Things tend to, or systems, they tend to move towards disorder. They like to go towards disorder. They don't want to actually go into order. The untidy room is kind of very stable. So remember this: high entropy states are kind of really stable. Like if you have an untidy room and there are people coming in and going out and you don't do anything, it stays untidy. I mean, it's not going to all of a sudden magically turn into a neat and clean room. So your room would remain untidy. It's if that state is, it's a very stable state. Okay, so an untidy room is kind of very stable. Uh, a low entropy state, on the other hand, a neat room is kind of very, very unstable. It's pretty unstable. Uh, I mean, as soon as you clean your room, you make it tidy. You set. I mean, everything is ordered and neat and nicely placed. Uh, it gets dirty very quickly. I mean, you're not making any special effort. Even if you're trying to keep it clean, it just automatically tends to move towards this more stable, untidy state. The same could be applied to any mechanical thing. Any, like if you buy a new car, uh, it would be very neat. Everything would be functioning very properly. All the mechanical parts uh, would be like, everything would be in its right place. But over time, it would feel that the car wants to go into a more stable state. It wants to go into a high entropy state. It's going to start breaking down if you start using it, and it's going to become untidy as well. The mechanical parts would stop working. So, and the more the mechanical parts, the more higher entropy state it is capable of reaching. So things kind of universal law. They tend to move towards, they like delta S positive. Because that's one thing. Is this concept clear to everyone? Zahib, is this
Yeah.
clear?
Yes.
Okay. So systems like to gain disorder. I mean, I'm not going to use the word disorder. I'm going to use the word entropy. They like to gain entropy. They like delta S positive. Okay, so that's a universal law. Um, and that could be applied. You have a house, you don't take care of it, it goes into a high entropy state. You distribute, like, and that could be applied to economics as well. Let's say you take uh, I mean, what happens to money? Like, for example, if there are 10 ATMs placed in the city, and you place 1 million rupees in each one of those ATMs. What happens to that money? It eventually gains entropy. uh, Somebody would take out 2000, somebody would spend it somewhere, and the money would eventually go into a very high entropy state, and it would no longer be neatly ordered. Like you had a million rupees each in each of those ATMs, but now it's everywhere. It's completely distributed, completely randomly distributed. It's a very high entropy. It eventually reaches a high entropy state. So the same concept could be applied in many different places, and the same concept could be applied to chemical reactions as well. That reactions that actually increase entropy, they kind of tend to happen more easily. Uh, and things tend to move towards entropy. Um, there's one thing that actually goes against. I mean, there's a universal law. Things tend to go towards a high entropy state. There's a thing which actually does the opposite as well, and that is basically the concept of life. Like wherever you see life, things actually tend to move to from an untidy state to a more tidier state. Uh, I mean, because who's cleaning up the room? It's basically you. Uh, what are your cells doing? What your cells are doing, they're taking random chemicals from everywhere, random substances, carbohydrates, proteins, and they're neatly ordering them in your body. And so they're trying to decrease entropy. So when they try and go and look for life, signs of life on another planet, what they're actually looking for is delta S negative. Because wherever delta S is negative, that means uh, there is life on that, because only that there's some intelligent species there that is trying to do the opposite. Uh, and as soon as life is gone, again delta S positive kicks in. So if something dies, everything goes into a high entropy state. It starts going into a high entropy state. The body starts to decompose. Everything happens. So, so just one thing that actually kind of momentarily opposes that, and that is the concept of life, which is delta S negative. Uh, so delta S positive, delta S negative. So the concept is clear, right?
Yes.
And we're now going to try. I said, but even the concept of, I mean, talked about life, but even that concept, it's like uh, when we say that systems like to gain entropy, the universal law is that it's always gaining entropy. Like even if there is life, uh, life would be making delta S negative, but at the same time, it would also be making delta S positive. Like humans build cities, so that is like delta S negative. I mean, they're putting things in order, but at the same time, they're also creating a lot of mess. Like that's global. I mean, because of those cities, there's going to be garbage dumps. There's going to be a lot of pollution. So at the same time, just to have that certain delta S negative uh, that the humans are doing. Uh, they're also at the same time creating a lot of delta S positive. So overall, uh, like planet Earth, it has life on it. Overall, planet Earth is actually moving towards a high entropy state. It's moving towards more disorder because whatever life that you have in that local space, it's trying to be delta S negative, but overall, it's producing a lot more entropy. So this systems, they like to gain disorder. And so now I'm going to just apply the concept to chemical reactions. So how do you? I mean, that's the first thing. I mean, entropy is not a big chapter. It just has a few. I mean, you just have to just conceptually answer a few things. First thing is figure out the delta S sign. So how do you figure out the delta S sign? Number one, look for a change of state. I said look for a change of state. If you're going from solid to liquid to gas, or gas to liquid to solid, okay, let's try and go from solid to liquid. Can anyone tell me what is the sign of delta S? Higher entropy or lower entropy? Gaining entropy or losing?
high.
So remember this: solids have very low disorder. I mean, they're very ordered, and gases they're highly disordered. They have very high entropy, and and liquids are in between. But they're not actually in between. Solids and liquids. The difference in entropy between solids and liquids that's uh, that's a smaller difference. But when you go from liquid to gas, that's a pretty large difference. So liquids are not exactly in the middle. Liquids are kind of closer to they're kind of closer to gases. I mean, you can see solids and liquids and gases. I did see a diagram somewhere. Just a second. So this one. Okay, that's a good one. Uh, Let me just copy it. So this diagram over here is kind of a representation of what's happening. Now, solids and liquids, that's not a very huge jump, but liquid to gases, that's a huge. This is highly disordered. Uh, and if something changes into a gas, I mean, things explode when things change into gas because of the higher pressure. So, so just remember that. So you can be asked to plot these entropy graphs. For example, I mean, we can do one for ice, and we are trying to increase temperature. So this axis over here is temperature. So can anyone tell me what would happen if I increase the temperature of ice? Would the entropy increase or not?
Increase.
Yes,
And would it constantly increase or not?
yes,
So now, just to clarify that, for example, I've got 2 cups of water, right? I've got a container that's full of water, and that's at 5 degrees centigrade, right? And I start to heat it, and the container reaches a temperature of, let's say, 60 degrees centigrade, right? Uh, so did the disorder change or not? Like,
no,
yeah, I mean, it didn't change much. I mean, still, I mean, visibly there is no difference. I mean, like if I showed you 2 containers of water, one was at 5 centigrade and the other one was 60 centigrade. I mean, you wouldn't know which one is hotter or which. I mean, but you would touch it and then you would know. But otherwise, it would be impossible for you to actually figure out which one is the higher. I mean, there's almost no change in disorder. So remember that. So remember that when you heat something, that doesn't mean disorder would change. I mean, does change, and it definitely increases, but almost negligible. ठीक है? Is this point clear as well?
Yes.
yes,
So the change is going to be very, very negligible. Just one second. So the change is going to be very negligible. And so, for example, if you take a metal at minus 100, right? There's a piece of metal, uh, and you start heating it, and it reaches, let's say its melting point is like 2000 degrees centigrade, and you start heating it. And now it was at minus 100, but now it's at 1500 degrees centigrade. Is there any change in disorder?
Not much.
Okay, not much. Like if you're heating a metal, uh, maybe if you can find. So if you're trying to heat a metal, let's look at this, right? Let's say this one is at minus 100 degrees centigrade. It's really cold, and this red hot one, is at 1500 or 2000 degrees centigrade. I mean, the particles are still arranged in exactly the same way. They're not. I mean, this hasn't really turned into disorder. Okay, so the point is, and I'm going to make the diagram for water. What's going to happen with water is, let's say this temperature over here is minus 10. Give it a value. Let's say we're starting at minus 10 degrees centigrade, right? So it's ice. Now, when you start heating ice, the entropy would slowly or very slightly increase. So that's the disorder. That's the entropy being measured. But once you reach 0 degrees centigrade, all of a sudden there's going to be this jump in disorder, right? So now it has changed into a liquid, and there's this increase in disorder, and then from 0 to 100, things kind of remain almost the same, just a very very gradual increase in disorder, not much. But as soon as you hit 100, what would happen? All of a sudden, there's going to be this massive increase in disorder, and then so there's going to be a massive increase in disorder. So this was where it was solid. This is where it was liquid, and this is where it's a gas. So remember that solids and liquids, the entropy doesn't really change much, because you have to imagine what disorder is. Disorder is how randomly, or like how disorderly the particles are. If you look at two liquids, they're still both liquids, so the disorder is pretty much the same. Uh, for gases, the disorder kind of changes a lot, because the problem with gases is, uh, like if you keep the pressure fixed, the gases expand. So remember this. Like if you don't allow them to expand, then the disorder pretty much remains almost the same. So remember that disorder increases if gases are expanding. Like your car seat, your airbags in your car. If you allow them to expand, there's going to be disorder. Uh, if you don't allow the gas to expand, there won't be any disorder. Is this point clear as well?
Yes.
ठीक है, Minhail, is this?
So
Yes.
is there such thing as a maximum disorder of an object, something?
No, it's if you keep on providing energy. You can theoretically you can just keep going on. I mean, there won't be any point. There's a point of zero entropy, which is zero disorder, but maximum there's no point. Like what's and do you know what zero? When would something have zero disorder?
Sub-zero?
Absolute zero, right? It's minus 273 when the particles would be in the form of a perfect crystal with absolutely no energy. So that's zero disorder. You remove all the energy, you take it to minus 273 or 0 kelvins, uh, which is not really an actual value. I mean, it's an interpolated value. So you can say that the substance is going to have absolutely no energy and the particles would be in a perfect crystal lattice. So is this all clear so far?
Yes.
I said, and also for gases, just remember that their disorder would increase only if you allow them to expand. The problem with liquids and solids is they don't expand. I mean, so gases can expand, but you can stop them from expanding. If you stop them from expanding, like if you stop your airbags from inflating, there wouldn't be any disorder, right? So so remember the change of state, solid to liquid to gas, and always focus on gas. Gases have really high entropy. So point number two is, okay, let's talk about point number two. When does entropy increase? So number two is it increases uh, when you have more gas modes formed. Okay, so that's when it's going to increase. So in a chemical reaction, if there's more gas that's being formed, for example, there is butane C4H10, and it's a liquid, and let's say the reaction is happening at a higher temperature. So, but let's say it's happening at a higher temperature, so it's in gaseous state, and it burns and it produces carbon dioxide and a water molecule. So how many water molecules? It's going to be 5 water molecules that it's going to produce, and it's going to produce 4 CO2 molecules. And let's assume that they're both, the reaction is happening at a higher temperature, so they're both in gaseous state. So the other thing is 4 plus, 8 plus 5, that's 6.502. So what's happening over here? What's happening is you've got 7.5 molecules of gas, right? And on the other side, it's changing into 9 moles of gas. So that kind of clearly shows that there's significant change in disorder happening. This delta S is positive, right? Is this clear?
Yes.
Similarly, number three. Number three is if something changes from solid to liquid or to aqueous. That's also delta is positive. Like if NaCl dissolves, and NaCl is a solid, you mix it in water, it dissolves, and it turns and dissociates into aqueous ions. So you got Na plus one aqueous, plus you have Cl minus one, which is also aqueous. So NaCl solid is dissolving and it's turning into aqueous ions. So when that happens, so when that happens, uh, so that's basically delta S positive as well. So is this clear? When you can figure out whether delta S is positive or not.
Yes.
I just
Yes.
so I'm going to do the first part now. Just we can just focus on the questions where you'll be asked to. This is the easy part. You'll be asked to figure out where are the entropy questions. 1 second. You'll be asked to figure out the sign of entropy change. Where's entropy? Okay, let's talk about this one. So I'm just going to where are the questions? Delta S. I mean, for example, this one is a difficult question, but probably they're asking what would happen for if addition polymerization is happening, right? So I'm just going to Google addition polymerization to see of alkenes. ठीक है, just figure out if there's an image of addition. This one, yeah, this one shows something. So this is addition polymerization of alkenes happening. You studied this in O levels and AS as well, probably. So you've got a bunch of alkenes, thousands of them, and they all join up to form this one long chain. So what's happening? Delta is positive or negative?
Negative.
ठीक है, negative. They're becoming more disordered. Sorry, more ordered. Uh, I mean, they were more disordered previously. They were gas molecules. They were all flying around. Here, let me just, we can just copy this on the board. Where's the board? So, just for the sake of examples, uh, so clearly, this is clearly negative. The molecules are, I mean, the alkene molecules are probably gaseous. So they're all randomly just flying around in gaseous state, highly disordered. So this state is a high entropy state. And this other state is more disordered. So delta S is it's definitely coming out to be negative. Is this clear? Minail, is this clear?
Yes.
Awesome. Awesome. Achha, then they've also in the question they've also I think talked about condensation polymerization in that particular question. What would happen for condensation polymerization? Now, if you look at condensation polymers, and let's say let's talk about polyesters. So let's think of polyesters. Can we see somewhere there? I mean, these are. So let's take this one. Okay, let's copy this. This is an example. I must have studied this in O levels. Okay, so let's copy this on a board. Is another example. So in this one, what's happening? What happens in condensation polymerization is you take two molecules, and what happens? What happens is that the OH and the H are lost, and they produce a water molecule, right? The H and the OH from the sides also get lost, and they produce a water molecule. So that means once a polymer is formed, there would be two water molecules that would be produced along with it. So is that delta is negative or positive? Like you had two monomers, and now you have a polymer plus two water molecules as well. So that kind of indicates that there are more particles being produced. So there's going to be more disorder. Is this clear? Did you get this? Ethan, Mohammed, is this clear? Zaib?
Yeah.
Okay.
Yes, sir.
So there would be two molecules are getting converted into three molecules. So that means there's an increase in disorder. As anyways, we're going to do some that was kind of a slightly difficult question. Most of the questions are going to be pretty similar and easier. Let me just. So for example, this one. Let's talk about this one. Mg plus O2 produces MgO. Is this delta S negative or positive?
Positive.
So
Negative.
okay, so that's negative because there was a gas and now it's turning into a solid. So there's a decrease in disorder. What about the second one? You had liquid water Is it they're six separate molecules. They've all joined up to form this one crystal. So that is what.
Negative.
Okay, that's also negative. What about the last one? Solid reacts with aqueous, produces aqueous, gas, water molecules. Okay, this one is going to be positive. There's an increase in disorder because there's a gas being formed, plus the number of particles are also increasing. So there's an increase in disorder. So that's number one. Again, predict the delta S for this reaction. What's the delta S? How many molecules?
Positive, because more.
Yep. So, and the reason is, I mean, they're all gases. The moles of gas increase. Okay, so the questions are going to be pretty similar if you know what the reactions are. Uh, then the questions are kind of be the kind of they would be easier, not that difficult. So just remember, entropy is disorder, and things like to gain disorder, and you'll be asked to figure out whether delta S is positive or negative. We'll do the rest tomorrow then, okay? So let's continue tomorrow.
Thank you.
Okay. Thank you.
Okay, take care.
Thank you.
Hafiz.
Allah Hafiz, sir.